Hello, and welcome to this webinar about permanent magnets and electromagnetic simulation. Today, we'll talk about how these materials and characteristics form the foundation of many modern electrical machines. From their core properties to practical applications, we'll walk through what makes permanent magnets so powerful and essential in everything from motors and generators to sensors and energy systems. At the end of this webinar, we will learn a simulation workflow to model permanent magnets, analyze their key properties, and understand their behavioral in world engineering application. In this quick but comprehensive session, our objectives are clear. First, we'll look at a brief history and define what permanent magnets are. Then, we'll explore the key magnetic properties that matter in electrical engineering: remnants, coercivity, and the energy product. In the third part, we will classify permanent magnets into major material groups: ferrites, Alnico, NDFEB, and SMCO, comparing their magnetic and mechanical performance. Fourth, we will explore the integration of permanent magnets in rotating electric machines, including surface and interior mounted topologies, and their influence on machine performance metrics like torque density, cogging, and thermal demagnetization risk. Then, we'll talk about key factors in selecting permanent magnets, evaluating material properties, cost, and thermal stability for reliable application performance. In the final section, we will present a software demonstration to apply the concepts discussed and showcase how to simulate permanent magnets in a practical engineering context. Permanent magnets are materials that produce a constant magnetic field without the need for external power. They operate based on the alignment of microscopic magnetic domains that, once oriented by an external magnetic field, remain locked in that configuration due to the material's intrinsic coercivity. Permanent magnets provide a stable magnetic flux with zero ongoing energy cost, making them ideal for passive or energy-efficient applications. In electrical engineering, they are usually used in motors, generators, magnetic bearings, and sensing devices. Their performance, however, is bounded by material limitations such as Curie temperature and mechanical fragility. Therefore, understanding the magnetic behavior and physical constraints of these materials is crucial for successful integration in dynamic electromagnetic systems. To evaluate the performance of a permanent magnet, we have to consider several key magnetic properties. Remnants refers to the residual magnetic flux density remaining in the material after the magnetizing field is removed. It indicates the maximum flux the magnet can contribute to the magnetic circuit. Coercivity is the intensity of the opposing magnetic field required to reduce this magnetization to zero. This reflects the material's resistance to demagnetization. The energy product represents the maximum energy density stored in the magnet, and it is a direct measure of how compact a magnet can be for a given application. Together, these properties define the BH hysteresis loop. Engineers often plot this loop at multiple temperatures to evaluate the performance under operating conditions, especially in high-temperature environments where demagnetization risks are heightened. Advanced design tools can simulate these characteristics under load to optimize magnet use in dynamic systems. Permanent magnets are typically classified into four main types, each with distinct characteristics and applications. Ferrite magnets made from iron oxide and barium or strontium carbonate are inexpensive and highly resistant to demagnetization and corrosion, but offer low magnetic energy density. Alnico magnets, composed of aluminum, nickel, and cobalt, provide excellent temperature stability and high remnants, though they are prone to demagnetization due to their low coercivity. SMCO, or Samarium Cobalt magnets, offer a balanced profile with high coercivity, excellent thermal tolerance, and good corrosion resistance, though at a higher cost. NBFNeodymium or neodymium iron boron magnets exhibit the highest energy product, making them ideal for high-performance compact applications. However, they are susceptible to corrosion and thermal degradation unless appropriately coated or alloyed. Understanding the trade-offs in cost, magnetic performance, and operating environment is critical when selecting a magnet type for a specific engineering application. Ferrite magnets, often referred as ceramic magnets, are composed of iron oxide blended with strontium or barium carbonate. They belong to the class of hard ferrites and are known for their high electrical resistivity, which helps reduce eddy current losses in AC applications. Ferrites are cost-effective, chemically stable, and intrinsically corrosion-resistant, making them ideal for large-volume, low-cost applications such as in loudspeakers, refrigerator seals, and small electric motors. However, their major limitation is their relatively low remnants and energy product, typically ranging from 1 to 4 megagauss Oersted. Therefore, ferrites are not suitable for high-performance electric drives, where compact size and high torque density are required. On the other hand, their thermal stability is acceptable up to approximately 250 degrees Celsius, and their corrosivity remains stable under moderate demagnetizing fields, which makes them a good choice in harsh environments with wide thermal fluctuations. NdFeB, or neodymium magnets, are the most powerful commercially available permanent magnets. They offer excellent energy density, making them perfect for high-performance applications like electric vehicles, wind turbines, and precision actuators. However, they come with downsides. They're expensive, vulnerable to oxidation, and can lose magnetism at high temperatures. Often, protective coatings or thermal design strategies are necessary to make them reliable in tough environments. NbFeB magnets offer energy products as high as 55 megagauss Oersted. They are formed by sintering or bonding neodymium, iron, and boron with small additions of dysprosium or terbium to improve high temperature performance. These magnets exhibit high remnant flux density and corrosivity, making them ideal for applications that demand high torque to weight ratio, such as electric vehicles motors, robotics, and wind turbine generators. However, NdFeB magnets are highly vulnerable to oxidation and corrosion. Therefore, they must be protected with coatings such as nickel, epoxy, or polymers. Thermal sensitivity is another concern. Standard grades may suffer irreversible demagnetization above 80 degrees Celsius. High temperature grades can perform up to 200 degrees Celsius, but at a higher cost and a reduced BR. In high-speed applications, mechanical stress must also be considered, as these magnets are vulnerable to chipping or fracture under vibration or centrifugal force. Samarium Cobalt magnets are part of the rare earth family and are prized for their high magnetic strength combined with excellent thermal and corrosion stability. Their energy products range from 20 to 32 megagauss Oersted. One of their standout properties is their ability to operate in environments exceeding 300 degrees Celsius, with some grades tolerating up to 350 degrees Celsius without significant loss in magnetic performance. This makes SMCO magnets ideal for aerospace, military, and oil and gas applications where both magnetic strength and extreme environmental tolerance are required. Additionally, unlike NdFeB, SMCO is naturally corrosion resistant and does not typically require protective coating. However, SMCO magnets are more expensive due to the cost and limited availability of cobalt and samarium. They are also brittle, and special care must be taken during handling, assembly, and bonding processes to prevent cracking or breakage under mechanical stress. Alnico magnets, composed primarily of aluminum, nickel, and cobalt, were among the earliest high-strength permanent magnets developed in the 1930s. These magnets have relatively high remnants, typically in the range of 1.0 to 1.35 Tesla, and excellent thermal stability, with Curie temperatures exceeding 800 degrees Celsius. Alnico magnets exhibit very low corrosivity, often requiring external mechanisms to maintain magnetic orientation in the presence of strong opposing fields. Because of their low corrosivity, they are also easily demagnetized and not ideal for dynamic applications involving magnetic reversal. However, their linear BH curve and stable output across wide temperature ranges make them ideal for precision analog sensors, flux gates, and certain types of instrument-grade motors. In motor design, Alnico is rarely used today unless temperature tolerance and linearity are prioritized over magnetic strength. They are typically cast or sintered and can be shaped into complex geometries. The physical shape and magnetization orientation of a permanent magnet have effects on its performance within an electromagnetic system. Common geometries include cylindric, block, arc, and ring shapes. In electric machines, arc segments are widely used for surface-mounted rotors, while trapezoidal or rectangular blocks are common in interior PM machines. Magnetization direction, axial, radial, or diametrical, must be selected based on the application. For example, radial magnetization provides uniform flux distribution in motors, while axial is often used in magnetic couplings and sensors. The effective air gap, aspect ratio, and positioning relative to the stator teeth also influence flux linkage, cogging torque, and torque ripple. Finite element method tools like EMWorks software allow precise modeling of these variables to optimize magnet geometry for performance, manufacturability, and cost. Engineers must also account for demagnetization curves in non-ideal shapes using correction factors or 3D simulation. In electric machine design, permanent magnets serve as a source of excitation, replacing the need for field windings and eliminating excitation losses. Two main topologies dominate: surface-mounted permanent magnet synchronous machines, SPMs, and interior permanent magnet synchronous machines, IPMs. SPMs offer high efficiency and a simple magnetic circuit, making them suitable for low-speed direct drive systems. IPMs embed the magnets within the rotor laminations, enabling flux weakening at high speeds and contributing to saliency-based torque, improving field weakening and control dynamics. In both cases, the choice of magnetic material, shape, and placement directly affects the machine's back EMF profile, torque density, demagnetization resistance, and cost. Designers often use parametric optimization routines and FEM co-simulation with thermal models to ensure reliable operation under loads, transient, and environmental variation. Integrating permanent magnets into electromechanical systems require a multidisciplinary design approach, combining electromagnetics, thermal analysis, mechanical integrity, and manufacturing constraints. From an electromagnetic perspective, the selection of magnet grade must align with the flux density requirements and temperature profile of the application. Engineers should use BH curves at elevated temperatures to assess potential demagnetization under load or fault conditions. Thermal management is equally critical. Magnets are typically the most temperature-sensitive components in a motor. Thus, cooling strategies must ensure the magnet temperature stays below its maximum operating point, often between 80 to 200 degrees Celsius for NDFEB and up to 350 degrees Celsius for SMCO. Mechanically, the magnets must withstand stresses from rotation, vibration, and assembly. Adhesives, magnet retention sleeves, or interlocking rotor topologies are commonly employed. Moreover, manufacturability, including magnet orientation during assembly and potential magnetization after installation, can introduce constraints that must be reflected early in the CAD and FEM modeling phases. These decisions directly impact efficiency, cost, and reliability of the final product. Magnetic simulations must be coupled with thermal and mechanical analysis to ensure performance stability under real operating conditions. For example, a thermal rise of 50 degrees Celsius can reduce the remnant flux density of NDFEB by up to 10%. Advanced simulations also allow the designer to test different magnetic topologies, V-shape, spoke, inset, and compare their performance metrics under varying load conditions. Through parametric sweeps, optimization algorithms can fine-tune magnetic dimensions, air gap length, and stator slot design for maximum system efficiency. In motor design, simulations typically focus on computing flux linkage, cogging torque, torque ripple, back EMF waveform, and demagnetization risk. Permanent magnets are foundational in a wide range of modern applications. In the transportation sector, traction motors for electric vehicles use high-energy rare earth magnets to deliver compact, high-torque solutions with excellent efficiency across variable speeds. In airspace, SMCO magnets are favored for actuators in high-temperature environments. In renewable energy, direct drive wind turbines rely on large diameter PM generators that eliminate gearboxes, improving reliability and reducing maintenance. Consumer electronics use miniature magnets in speakers, vibration motors, and sensors. Magnetic encoders and resolvers, which are vital for precision motion control, depend on stable magnet behavior under temperature and mechanical stress. Even in industrial automation, brushless DC motors with embedded magnets dominate due to their long lifespan and high control resolution. These examples highlight the versatility of permanent magnets, but also the importance of precision design to prevent overengineering, cost overruns, or premature failure in mission-critical applications. In summary, permanent magnets are indispensable components in modern electrical engineering, especially in the design of high-efficiency electromechanical systems. We've covered the fundamental magnetic properties, remanence, coercivity, and energy product, and their significance in real-world performance. We analyze major magnet types, including ferrites, Alnico, NDFEB, and SMCO, understanding their unique strengths, limitations, and ideal applications. We examined how shape, orientation, and thermal conditions influence performance and the importance of simulation tools in verifying magnetic behavior within complex systems. Ultimately, successful use of permanent magnets depends on harmonizing electromagnetic, thermal, mechanical, and economic constraints to meet specific application requirements. As technology evolves, particularly with increasing electrification of transport and automation, the role of permanent magnets would only become more critical. Continuous advancements in materials science and simulation capabilities will empower engineers to design smarter, smaller, and more reliable systems. Now, let's use EMWorks software to simulate a magnetic system and observe a practical application of the concepts we've covered. In this part, we'll walk through the simulation of a permanent magnet wheel using a Halbach array configuration in EMWorks Emacs software. As discussed earlier, permanent magnets play a critical role in modern electrical machines, especially in motors, generators, and magnetic levitation systems. The goal here is to demonstrate how this Halbach array used in this magnet wheel can be modeled and analyzed using finite element methods in Emac. What is a Halbach array? Let's begin with the basics. A Halbach array is a special arrangement of permanent magnets that strengthens the magnetic field on one side while nearly canceling it on the opposite side. This phenomenon is achieved by orienting the magnetization of each magnet at a specific angle to its neighbors. This creates a highly directional magnetic field. Halbach arrays are widely used in brushless motors, maglev trains, and particle accelerators because of their field concentrating effect and efficiency. In this study, we use a 12-magnet Halbach array to analyze the resulting magnetic field behavior. Here is the model: a circular arrangement of 12 identical permanent magnets, each oriented to follow the Halbach sequence. This sequence is set to enhance the field on the wheel's outer surface. The model is built and simulated in EMWorks EMAG using full 3D finite element analysis. The geometry represents the magnetic wheel, and the simulation will focus on understanding the step-by-step simulation process and options we have in different studies and available results. The main goals of this simulation are to visualize how magnetic flux flows through and around the magnet wheel and the steel plate, to measure magnetic field strength, the B field, across various regions, to measure the force between the wheel and the steel that stick to it, to evaluate how well the field is concentrated on one side and how much leakage occurs on the opposite side. These insights are valuable for improving the design of efficient electromagnetic devices. Let's walk through each step of the simulation process in EMAG. Open EMAG and begin by creating a new project. Then, define the project geometry. You can either build the geometry of the Halbach wheel inside EMAG using the powerful CAD tool powered by Autodesk Inventor, or import it from an external CAD software. Make sure each magnet is placed at 30-degree intervals for 12 magnets in total. As you can see the magnets, the wheel and the plate is ready in this project. Define the study type as transient simulation to be able to model the motion and rotation. Set the start time, end time, and time increments, as they are one of the most important things that affect the result's accuracy. Now it's time to assign materials. Select a suitable permanent magnet material, such as neodymium iron boron, from the comprehensive built-in material center and assign it to each magnet. Then define the surrounding air region. Let's set the magnetization directions. For each magnet, define the coercivity vector. Follow the Halbach array pattern where each magnet is rotated appropriately to create the desired field distribution. For setting the magnets, you need to define the local coordinate systems, as you can see here. Then set the direction due to the selected coordinates. Next, define boundary conditions. Apply boundary conditions like normal flux or tangential flux for the geometry. Let's mesh the model. Generate a finite element mesh with the desired resolution. The Mesh Control tool will help you define the precise mesh layers within the objects. You can review the mesh by plotting it and revise the mesh resolution if it is needed. Let's run the simulation. Once everything is set, validate the model to ensure that there are no setup errors, then run the solver. You can monitor solver progress and ensure conversions in the message window. Let's look at post-processing results. Use EMAG's built-in tools to visualize the magnetic field, display magnetic flux lines and B-field vectors, create color maps showing field strengths. You can also extract quantitative data such as maximum flux density or flux across a cross-section. In the results table, you can plot the force attached to the wheel to the plate in different time steps. Here are the results from the simulation. As expected, the Halbach array produces a strong magnetic field on one side with a much weaker field on the other. The flux density plot confirms this asymmetry. The field vectors clearly indicate field lines being compressed on the active side and dispersed elsewhere. To summarize, we have seen how to simulate a Halbach array in EMAG from start to finish. The software provides an efficient, user-friendly platform for finite element analysis of magnetic systems. This kind of analysis helps optimize magnetic designs by providing clear insights into field behavior. Thank you for your attention. We'll now take any questions you may have. Please feel free to ask your questions in the chat box. And if you would like to learn more, please feel free to contact us at www.emworks.com.